This module will cover three-dimensional finite wings. So far, we have only considered 2D airfoils, which are also called infinite wings. The key difference between a finite wing and an airfoil is that a finite wing has wingtips. At first, this may seem obvious or trivial, but the presence of wingtips completely changes the nature of the flow field. This section introduces the aerodynamics associated with wingtips. Notation-wise, 2D airfoils use lowercase letters and subscripts. 3D finite wings will use uppercase letters and subscripts. Here we'll define some terms used to describe a wing's geometry. First is the planform area S. It's the reference wing area used in computing aerodynamic coefficients. It is the area projected by the wing onto a flat surface. You can also think of it as simply the top view of the wing. And note, it's not a wetted surface area. Second is the wingspan, given the symbol B. It's the horizontal straight line distance from wingtip to wingtip. Third, the root chord, C sub r, and the tip chord, C sub t, are the distances of the chord line at the root and the tip, respectively. The ratio of the tip to root chord is called the taper ratio. A rectangular wing has a taper ratio of 1. A delta wing approaches a taper ratio of 0. Fourth, the mean aerodynamic chord. This is a theoretical chord for an imaginary straight untapered wing which has the same force vectors as the actual wing throughout the speed range of concern. The true mean aerodynamic chord is difficult to compute for many modern aircraft wings since they can be tapered, swept, elliptical, or otherwise irregular. Simplistically, you can think of it as the average chord length for the wing. Fifth, sweep angle, which uses the Greek symbol for capital lambda, can be defined in reference to the leading edge or the quarter chord line. The quarter chord sweep angle is illustrated. Sweep aft is normally considered positive and sweep forward is considered negative. And finally, we have the sixth term, the aspect ratio. This is a dimensionless parameter that indicates how long and skinny or short and stubby a wing is. In general, it's defined by the equation b squared over s. For a rectangular wing where s is just b times c, this reduces to b divided by c. We'll now compare the lift distributions of a 2D airfoil and a 3D wing. In both cases, there is a relatively low pressure on the upper surface and a higher pressure on the lower surface. In the case of the 2D airfoil, the wall, or infinitely long span, prevents any flow around the wingtips, so the lift distribution is completely uniform across the span. In the case of the 3D wing, the flow on the lower surface sees the flow on the upper surface, and the high pressure air from the lower surface wraps around the wingtip in an effort to move to the region of lower pressure. The result of this is a vortex at each wingtip and a non-uniform lift distribution. These wingtip vortices are typically very large and will completely envelop the wing. The wing therefore sees a downwash from the wingtip vortices, stronger at the tips, a little weaker in the middle. In addition, these vortices will trail behind the aircraft and travel downwards in the atmosphere. These trailing vortices can last in the atmosphere for minutes, depending on atmospheric conditions and the strength of the vortices. These vortices won't be present if there are no wingtips. They also will not be present if the wing is generating zero lift, where equal pressures on lower and upper surfaces exist. Let's give the downwash velocity the symbol W and superimpose it on the free stream velocity V infinity. Epsilon is the downwash angle, and V effective is the effective velocity the wing experiences due to the downwash from the wingtip vortices. The downwash velocity superimposed on the free stream velocity results in an effective velocity and an effective angle of attack, as shown. This is the effective flow field being seen by the wing. Notice, due to the presence of downwash, the lift vector has been tilted back such that the effective lift vector, L prime, is perpendicular to the effective velocity. However, by definition, lift is perpendicular to the free stream velocity and drag is parallel to the free stream velocity. That means there is a component of L prime parallel to the free stream velocity. This component of force is called induced drag, or drag due to lift. Not shown in the diagram is how the drag vector also gets tilted. The result of that is there is a component of the effective drag in the direction perpendicular to the free stream velocity. So the downwash from the wingtip vortices does two undesirable things. It increases drag and it decreases lift. Our goal is to come up with an expression to calculate the induced drag. From simple geometry, we see that sine of epsilon is di over L prime, which is approximately equal to di over L. Assuming a small downwash angle, it follows that sine of epsilon is approximately epsilon and that L prime is approximately L. Therefore, induced drag is L times epsilon. And it can be shown that the downwash angle is given by epsilon equals CL divided by pi times E times the aspect ratio. Here E is defined as the Spanwise efficiency factor, and its value can range from 0 to 1. It is a shape parameter which indicates how elliptical the lift distribution is. If the lift distribution is perfectly elliptical, then E will equal 1. All non-elliptical lift distributions will have span efficiency factors less than 1. It's clear from this equation that an elliptical lift distribution is the most desirable. The reason this occurs is the elliptical lift distribution results from an optimum uniform downwash distribution across the span. In the end, we can make all the substitutions and we're left with the equation in the yellow box. This is a very important result. It tells us several significant things about how to minimize induced drag. First, minimize CL. If the airplane is flying in straight, level, unaccelerated flight, it generates just enough lift to overcome weight. Therefore, weight equals lift equals CL times the dynamic pressure times the wing area S. Therefore, for a given wing size, you can minimize CL by lowering the weight. The lighter the plane, the less CL required. Also, you can fly fast. The faster you fly, the more dynamic pressure and the less CL required. Put the two of these things together. Where are wingtip vortices the strongest and induced drag the greatest? The answer is on takeoff. The airplane is heavy, it's flying slowly, and it's generating extra lift to climb. This is the key reason for traffic spacing at airports. An aircraft taking off needs to give the vortices from the aircraft in front of it the chance to dissipate. Getting caught in another plane's vortices can be disastrous. Second, we can maximize the span efficiency factor E. Third, maximize the wing's aspect ratio. And fourth, disrupt the wingtip vortices. There are a few ways to maximize the spanwise efficiency factor E. First, vary the length of the chord such that the wing has an elliptic planform. The Spitfire is a prime example of an airplane with this design feature. Second, geometric twist. Vary the angle of attack of the airfoils along the span. A wing with tips at a lower angle of attack than the root is said to have washout. This has additional benefits besides the shaping of the lift distribution. If the tip has a lower angle of attack, it will tend to stall later than the root. This is desirable because ailerons are located near the tips. Delaying tip stall is therefore important for roll control at high angles of attack. Third, is aerodynamic twist. Vary the actual airfoil shapes along the span. For example, the root might have a NACA 2414 airfoil and the tip may have a NACA 0009 airfoil. Maximizing the aspect ratio minimizes the effects of the wingtips and reduces induced drag. That's why gliders and the U-2 have large aspect ratio wings. Fighters, on the other hand, cannot afford to have large aspect ratio wings because they need to be highly maneuverable. They overcome the penalty of induced drag by flying fast and having a lot of thrust. End plates, or winglets, are devices on the tips of the wing which particularly disrupt the vortex. This has essentially the same effect as increasing the effective aspect ratio. And you'll see many different approaches to designing end plates. Some go up, some go down, and some do both. Another way to disrupt wingtip vortices is to fly in ground effect. When an aircraft is near the ground itself disrupts the wingtip vortices. The result of this is reduced induced drag and increased lift. There are practical limitations to flying close to the ground. You can see some designs over the years of flying an aircraft just above sea level. Finite wing geometry with wingtips has introduced another form of drag that we called induced drag or drag due to lift. Skin friction, pressure, and wave drag, if you're supersonic, still exist. In summary, the drag coefficient for a finite wing, denoted as C sub d with capital letters, is written with the following equation. Little cd has the components of the fuselage, the propulsion, and the wings all embedded into the one parameter C sub d with lowercase scripts. Graphically, the various drag components can be represented on a drag polar. Skin friction is basically always present and remains fairly constant with CL or angle of attack. Pressure drag becomes significant at higher CL or angle of attack as the streamlined body becomes more of a blunt body. Induced drag grows as the square of CL. It's what makes the total drag a true polar. We saw that downwash from the wingtip vortices altered the local flow field seen by the wing. This had the effect of increasing drag and decreasing lift. As was done for the drag coefficient, we would like to modify airfoil lift data to adjust for the effects of the wingtip vortices. Qualitatively, the effect of downwash on the lift curve is shown in the graph. First, for a given angle of attack, the finite wing produces less lift than the 2D airfoil. This is due to the decreased effective angle of attack seen by the wing due to the downwash. Second, the angle of attack at zero lift is the same for an airfoil and a 3D wing. If the wing is not generating lift, then no wingtip vortices are formed. In effect, the finite and infinite wings behave the same in this case. Third, the key difference between the curves is a difference in the lift curve slope. The lift curve slope for a 2D thin wing is simply 0.11 per degree. It can be shown that the lift curve slope for the finite wing is given by the equation shown. CL alpha is a 2D airfoil lift curve slope, E is the Spanwise efficiency factor, and aspect ratio is AR. The units of this equation are inverse degrees. The 57.3 is a degrees to radians conversion. Note what this equation says. Again, as aspect ratio increases, the wing behaves more like an infinite wing. The limiting case is an infinite aspect ratio where the 3D slope approaches the 2D slope. Fourth, below stall, the lift curve is simply a straight line. Therefore, CL for a finite wing can be easily calculated using the equation shown. Fifth, capital subscripts distinguish the finite wing lift coefficient and lift curve from that of an airfoil. While a low CL does result in a lower CD, airplanes do need to fly slow, for example, landing. In that condition, a high CL is needed. The resulting added drag can even be beneficial. That's the case for aerobraking. The slowest speed an airplane can fly in straight and level flight, where lift equals drag, is the stall speed, and it occurs at CL max. The equation for stall speed is derived as shown. In order to decrease the stall speed, a high max lift coefficient is desirable. An increase in the planform area S will decrease the stall speed. Also, recall that maximum lift coefficient is a function of Reynolds number. All else constant, an increase in altitude, which decreases the density, will result in a decrease in Reynolds number. Therefore, the max lift coefficient goes down with altitude. The aircraft stalls at a higher equivalent or true airspeed. Next, we'll cover high lift devices. Since we are limited in how slow we can fly by the stall speed, it should be clear from the previous equation that we would like to have as high a CL max as possible. Maneuvering, slow speed flight, and landing all require high lift coefficients. Basically, high lift devices are used to increase CL max. In order to provide lift coefficients greater than the maximum lift coefficient of a given airfoil, it is necessary to resort to special hardware. Devices of this type are boundary layer control, slats, and flaps, which can be both at the leading and trailing edges. Boundary layer control devices are suitable for low speeds, while flaps and slats are suitable for both high and low speed applications. Numerous variations of these devices have been proposed and are used on operational aircraft. Each type will be defined and their individual effects on an aircraft discussed briefly. Increasing the maximum lift coefficient of a wing can be accomplished by any one or combination of the two fundamental methods. The first is to increase the camber of the wing. The second is to delay separation through some means of boundary layer control. In addition, the total lift created by the wing can be further increased by increasing the wing area. An increase in camber is accomplished primarily through use of flaps. Flaps are high lift devices which are basically hinged leading or at the trailing edge wing sections. Trailing edge flaps are normally 15 to 25% of the chord, although they can be found up to 40% of the chord. Several arrangements are commonly used. The basic type of trailing edge flaps are shown here. The plain or simple flap is a simple hinged portion of the wing trailing edge. The split flap is essentially a plate deflected from the lower surface of the wing. The slotted flap is similar to the plain flap, but the gap between the main wing section and flap leading edge is given a specific contour so that the high energy air from the lower surface is deducted to the flap upper surface when the flap is deflected. The high energy air from the slot re-energizes the upper surface boundary layer and delays separation. The Fowler flap arrangement is similar to the slotted flap. However, when extended, it lowers and translates aft, thus increasing wing area as well as camber. Because of the unique movement of this type of flap, the mechanism is quite heavy and complicated and therefore may not be practical for certain aircraft applications. The effectiveness of flap on wing configuration depends on many factors. One important factor is the amount of wing area affected by the flaps. Since a certain amount of wingspan is normally reserved for ailerons, the actual wing maximum lift properties will be less than that of the flap two-dimensional section. Recently, attempts, some more successful than others, have been made to increase total aircraft lift coefficient using full span flaps in conjunction with spoilers for roll control. There are many variations in the design of leading edge flaps, which are also sometimes called slats. The Kruger flap is a popular leading edge flap. Many aircraft combine flaps and slats. The effects are both increased camber and increased chord length. You can see on the right diagram just how different the wing becomes when it transitions from its clean configuration to its full landing configuration. The main goal of boundary layer control is to energize the boundary so it will stay attached longer, thus increasing CL max. Slots and slats are aerodynamic means of effecting boundary layer control. Boundary layer control may also be accomplished by artificial means such as blowing air provided by a compressor over the wing, or by drawing the low energy boundary layer through the surface of the wing by some suction device. A fixed slot is an aerodynamic boundary layer control device since it takes high energy air from the lower surface of the wing and ducts it through the wing into the low energy boundary layer on the upper surface. In doing so, it delays separation and allows higher lift coefficients to be developed. A slot is relatively ineffective at low angles of attack, but becomes very effective at high angles, thus improving the high lift characteristic. Slots are used only on very slow speed aircraft since they cause very high drag at high speeds. A slat operates on the same principle as a slot, except that it is located near the leading edge and acts like an additional airfoil in front of the basic airfoil. Its function is to direct airflow over the leading edge of the airfoil. Fixed slats also cause high drag at high speed. A slat may also be of the movable type, which remains retracted at high speed and extends at low speed and high angles of attack. This increases the wing area slightly, as well as increases the flow over the upper surface of the wing. Another technique for energizing the boundary layer is upper surface blowing. The purpose of upper surface blowing is to inject the boundary layer with high energy flow. This high energy flow can come from any one of several places. As seen in the split flap, Fowler flap, and leading edge slots and slats, the high energy flow can come from the lower surface of the wing. It could also come from high pressure air vented from the engines, or the engine exhaust itself could be blown tangentially over the top of the wing. The purpose of upper surface suction is to draw the low energy flow near the surface out of the flow, leaving only the high energy flow in the boundary layer. This is accomplished by drilling thousands of tiny holes in the surface of the wing and applying some sort of suction. Again, this has the effect of delaying separation and increasing the maximum lift coefficient and stall angle of attack. Although they are not generally considered high lift devices, vortex generators also prevent separation aerodynamically by energizing the boundary layer. These devices are rows of small vanes placed perpendicular to the surface of an aircraft, each acting like a small wing whose wingtip vortices brings high energy air from the outside the boundary layer down into the boundary layer, thus re-energizing it. These are typically after-designed band-aids which are added to correct an unforeseen flow separation problem. Vortex generators normally add little toward increasing maximum lift coefficient. They are generally used to prevent local areas of separation, such as in front of an aileron, which causes the flow over the aileron to stay attached to a higher angle of attack than the rest of the wing. The strategic placement of vortex generators is in general an art rather than a science. And here's some more pictures of vortex generators at various positions on different aircraft. We've talked a bit about stall. We've also talked about wing planform shapes. Here's some pictures to show the stall patterns of various planform shapes. For elliptical wings, the whole wing basically stalls at the same time. Rectangular wings, like the Piper Cherokee 6, stall first inboard, then work their way outboard as angle of attack increases further. Stalling inboard first has the safety advantage of maintaining roll control. Moderately tapered wings are similar to elliptical wings in that the whole wing basically stalls at the same time. Highly tapered wings stall at the tips first. That means roll control will be lost. Pointed tip wings and swept-back wings also suffer with roll control at stall. However, we'll see benefits to these planform shapes later when we cover high-speed aerodynamics. In summary, we learned that 3D wings generate tip vortices. The downwash produces lift-induced drag. To minimize induced drag, either lower the weight, fly faster, maximize span efficiency factor, maximize aspect ratio, and/or disrupt the wingtip vortices with end plates. For a given angle of attack, the finite wing produces less lift than the 2D airfoil. The angle of attack at zero lift is the same for a finite wing and a 2D airfoil. The lift curve slope of a finite wing will be less than the lift curve slope of a 2D airfoil. Since slow flight is limited by stall, we need a high CL max as possible. Providing lift coefficients greater than the max for a given airfoil, we can use boundary layer control, slats, flaps, or vortex generators. In the next module, we'll examine lift and drag of the whole aircraft.